Good morning, afternoon, evening, whatever time it is when you are watching this trig. So we are continuing on our exploration of conic sections. Last week we talked about parabolas. This week we are moving on to ellipses. So what exactly is an ellipse? So an ellipse is defined as the set of all points. You notice this is a common beginning to our definitions so far. We're defining them as the set of all points that are something. So, like a circle is the set of all points equidistant from a single point. An ellipse is the set of all points in a plane. So this is a two-dimensional figure, that's what in a plane tells you, whose distance is from two fixed points in the plane have a constant sum. So we've got set of all points in a plane whose distances from two fixed points in the plane have a constant sum. So that constant sum is going to be really important to us. The fixed points are called the foci. You'll also hear people say foci. This is plural. Means more than one, so there's two of them. If you're talking about just one of them, singular, is focus. So the fixed points are our foci. And we got some other points that we need to talk about, some other parts of an ellipse to talk about. So we have a focal axis. And this is just basically a line through the foci. And you'll hear me say foci, foci. I switch back and forth. So then we have the center. And that is the point on the focal axis. Midway between the foci. One more word. And the vertices. That's plural of vertex. So the vertices are the points where the ellipse intersects its axis. So let's see, what does all this look like when we put it together into one shape? So this is a basic diagram of an ellipse. You'll see we have a minor axis that we didn't mention in our vocabulary. The minor axis is just the longest distance across the shortest side. The major axis or focal axis goes through the two foci, and it is the longest distance also from the longest way across. And then if I turn perpendicular to that, I should find the minor axis. So any point on this diagram, like I have this point right up here, xy, if I measure the distance from this focus to the point and then measure from the other focus to the point, add that up, I'll get the same distance as any other point. So I could put another point here. This would be x2, y2. If I measure the distance to one focus and the other focus, add that up, I'll get the exact same measurement as I did with the first point. So that is how we define an ellipse. Is here are all the points needed to make it, because they're all the same distance when you add up the distances between two points in a plane. So make sure you go ahead and copy this diagram down into your notes. And let's talk about a couple other things. So let's talk about the standard form of the equation for an ellipse. So we've got generally two different versions of these. So we can have our equation for one that has its focal axis, which is the longer one, right? We can have the focal axis either in the x orientation or in the y orientation. So if we want to have ours with the x-axis, orientation for our focal axis versus y-axis for the focal axis. So if I have my x-axis for the focal axis, the standard form looks like this: x squared over a squared, which is just some number. It's related to the size of the parabola. We'll find out more about that in just a minute. Plus y squared over b squared equals 1. So this is going to be centered at 0, 0. That's the simplest form. Centered at 0, 0. It uses the x and y axes for its minor axis and major axis, or its focal axis and minor axis. So focal axis and major axis, those are interchangeable terms. So if I want to switch it and have the focal axis or major axis now going vertical with the y-axis, it's basically just the inverse of this, so you switch your x and y positions. And the standard form is y squared over a squared plus x squared over b squared equals 1. So now let's get into what do all these letters mean, how do we find them when we're given different information, and we'll talk about ellipses with the center at 0, 0 first, and then we'll talk about ellipses with the center anywhere. If we have the option, we will always default to centering our ellipse at 0, 0, because that's the easiest way to do all the math. Okay, copy this down and moving on. Okay, so the stuff we're about to write down is how you find all the different pieces of an ellipse. So, if I tell you that the ellipse has a center of 0, 0, these are the relationships that you're going to use to find each of the different things. The cool part about using the center as 0, 0 is that your foci are going to be equidistant from each other because they're equidistant from the center. So they're just going to be opposite of each other. So if I tell you one foci is 2, 0, the other one has to be negative 2, 0. Okay, so we're going to do two different sides here. We're going to do our x-axis for our focal axis. Or y-axis. No z-axis because we're not in 3 dimensions, just 2 dimensions. Okay, so your standard equation for an ellipse with center 0, 0 and its focal axis in the x-axis is going to be, like we just wrote down, x squared over a squared plus y squared over b squared equals 1. So in this, we're going to say there's this other point C that is our foci. And our foci are going to be plus and minus C and 0. So this means you've got 2 points, positive C, 0, and negative C, 0. It's not plus or minus, it's plus and minus, it's both of them. So then our vertices are going to be same thing, plus and minus a 0. So when you see the prefix semi, that means half. So if I have half a circle, it's a semicircle. So half of the semi-major axis the length of it is A, which tells me the major axis goes from vertex to vertex through the center, and if it is at point A, that's the distance. Give myself a little more space. The length of half of the semi-minor axis again, semi means half, is going to be B. And then there's going to be this thing we'll talk about in a minute, and I'll give you a diagram of it, but we're going to write it down first. The Pythagorean relation. A squared, not the Pythagorean theorem. This is the Pythagorean relation for this specific type of ellipse. A squared equals b squared plus c squared. Looks similar to the Pythagorean theorem, but it's not. Okay, I'm going to draw a diagram in a minute and show you where all of these things come from. Let's write down the same thing, but for the focal axis being the y-axis. So our formula is going to be the inverse. It's going to be y squared over a squared plus x squared over b squared equals 1. So the foci should be flipped over, right? It should be 90 degrees to what it was. So the foci are going to be 0 plus and minus c. Our vertices, so remember that's plus and minus, just like here. We have plus C0 minus C0. We're going to have 0, positive c, and 0, negative c. The vertices are going to be flipped over again. So these are 0, plus and minus a. Our semi-major axis, half the length of the major axis, is going to be a, again. Half the length of our minor axis, or semi-minor axis, is going to be b, again. And our Pythagorean relation is going to be a squared equals b squared plus c squared. So let's draw a little bit of a diagram of each of these. So we're going to draw the best ellipse that we can and then label some of these points so that we know where some of this is coming from. So I'm just going to draw an XY axis right here. So the first point I'm going to put in is my vertices, not my foci. That's just, I'm going to draw this one. So my vertices for this are negative a, 0. So I'm going to go here and here. So this is negative a, 0, and positive a, 0. Then I'm going to put in my minor vertices for the minor axis. The minor axis goes, this was my x, that's my major axis, my focal axis is my y. I'm going to put in my other one, so this one is going to be 0, b, and this is going to be 0, negative b. Then my foci are going to be located somewhere along here. Here and here. So these are the points. These are just approximate because this is a diagram. Negative c, 0, c, 0. So your vertices will always be outside of your foci. So now I've got some points drawn in here, and so then I can give a quick little sketch of an ellipse. And as usual, this is not perfect, and that's okay. So the Pythagorean relation, if I draw a triangle, this length right here, this is my semi-minor axis. Which is half of my minor axis, right? The full thing is from one side to the other would be the full minor axis. This is the semi-minor axis, so that is length b. From here to here, that is length c. You could also call that the semifocal length because it's half of the distance between the two foci. And then we've got this other one from here to here. And that is the same length as a. So, if we remember our Pythagorean theorem, the square of the hypotenuse is equal to the sum of the squares of the other two sides. In this case, a is sitting in on our hypotenuse. So it has to be a squared is equal to b squared plus c squared. And that'll come up later. But this relationship will hold for all ellipses. So if I drew an ellipse in the other orientation, so for our focal axis being our y-axis, our ellipse goes with our major axis going up and down. So then we'd have our vertices being these points. So this one would be 0a. This one down here would be 0, negative a. We would have the minor axis having its vertices over here. So this would be like b0, negative b0. My foci would then be on the y-axis because that's our focal axis for this one. So my foci would be like somewhere around here, 0, c, somewhere around here, 0, negative c. And then when I draw this one in, it looks something like that. So I could draw my same triangle here. This is C. This is B. You see my triangle flips. And then this is A. So then my Pythagorean relation is still A squared equals B squared plus C squared, but my B and C have flipped from the x-axis and y-axis to their opposite. Okay, let's do a real quick example. I'm going to give you an equation, and then we're going to use that equation and the stuff that we just wrote down in this little table to find the coordinates for the vertices and the foci. Okay, example. Find the vertices and foci. Okay, so our equation is 4x squared plus 9y squared equals 36. And we notice that our standard forms were something like x squared over a squared plus y squared over b squared equals 1. So the important part here is that this is equal to 1. And we notice over here this is not equal to 1. So, first step, we're going to divide everything by 36 on both sides so that we can get this into standard form. So divide by 36. And the reason I didn't just do like one thing, divide by 36 like that, is because my standard form doesn't have it in one fraction. It's got two fractions. So I'm dividing each fraction by 36 because it's going to be way easier. Alright, so simplify 4 over 36 to x squared over, if I divide 4 out of each of those to simplify, I'm going to get 9 plus y squared over, divide 9 out of each of those, I get 4 equals 1. So then I look and see, I've got two fractions. Is this going to be in having my focal axis in the y orientation or the x orientation? How can I tell just by looking at this? Well, if I look at this, I want to look at the denominators, because the larger number is right here with the x squared. The focal axis is in the x-axis direction. So larger denominator under x squared equals focal axis is in x-axis. So that's very good information. That's going to tell me where my a squared and my b squared are. So if it's in the x-axis like I wrote up here, this is the x-axis standard form. A squared is underneath x, b squared is underneath y. If it was the other way around and the largest number was under y, then a is under y and b is under x, which would make this opposite from what we're going to do. So that tells me that this is a squared right here, and this is b squared. So a squared equals 9, which tells me a is the square root of 9, 3. This tells me that b squared is 4, and b is the square root of 4, which is 2. So then I can think, well, okay, my vertices are going to be plus and minus a, 0. So that means my vertices are 3, 0, and negative 3, 0. So I've got a and b, but I need c to find my foci. So I'm going to use that Pythagorean relation that we talked about, because I have a, I have b, I need c. So if I have a and b, and I have the Pythagorean relation, I can find c. So my Pythagorean relation is a squared equals b squared plus c squared. So now I can plug a and b in and then solve for c. So let's plug these in and solve. So I get 9 equals 4 plus c squared. Subtract 4 from both sides, and I get 5 equals c squared. Solve this by square rooting both sides, and I get that c is equal to the square root of 5. You can leave it as square root of 5 instead of doing the square root and getting that long decimal. So you can tell me that the foci are at square root of 5, 0, and negative square root of 5, 0. I am okay with you telling me that the answer is plus and minus square root of 5, 0. That's our foci. And I am okay with you telling me that the vertices are plus and minus 3, 0. So that is how you find the vertices and the foci of an ellipse. Once you have A, B, and C, then you can find all the other things that we wrote down on our table. So you can take this same idea, and I could tell you the foci and maybe the length of the minor axis, and you can use that and the Pythagorean relation to go backwards and find the standard form of the equation. So let's write down the key features of an ellipse that doesn't have a center at 0, 0. Okay, so these are going to be ellipses that don't have 0, 0. So we call the center HK. So standard equation is going to be x minus h squared over a squared plus y minus k squared over b squared equals 1. And our focal axis is going to be y equals k. So this is still with a long direction in the same orientation as the x-axis. But the actual focal axis is moved away from just the line y equals 0, which is the x-axis. So our foci have shifted. So it's going to be h plus and minus c, comma, k. Our vertices along the major axis, their coordinates are h plus and minus a, comma, k. So the foci and the vertices are on the same line with each other. They're on the major axis together. So the length of the semi-major axis is still a. The length of the semi-minor axis, so half, is still b. And our Pythagorean relation is still a squared equals b squared plus c squared. So really, four things changed, three things didn't. So now for our major axis in the y direction orientation, our standard form of our equation is going to be y minus k squared divided by a squared plus x minus h squared divided by b squared equals 1. So our focal axis is going to be x equals h. Our foci are going to be h, comma, k plus and minus c. Our vertices are going to be h, comma, k plus and minus a. And again, our semi-major axis is a, didn't change, semi-minor is b, didn't change, and our Pythagorean relation is still a squared equals b squared plus c squared. Okay, let's do one more example. And let's find the equation of an ellipse now. But we're going to do one that's not centered at 0, 0. So I'm going to move and find some empty space. Okay, this example is going to be about finding the equation of an ellipse. So find the standard form. of the equation for the ellipse whose major axis has endpoints -2, -1, and 8, -1, and whose minor axis has length 8. Okay, so I'm going to start thinking about the things that we've written down. Major axis endpoints are along what direction? So I'm looking, the x value changes, the y value stays the same, which tells me they are going horizontal, so they're going in the direction of the x-axis. So we know the equation has to be of the x-axis, major axis, focal axis variety. So its standard form is going to look like this: x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. So center is hk. We know it's not 0, 0. We know that A is the length of the semi-major axis. We know that B is the length of the semi-minor axis. So it tells us the minor axis has a length of 8, but I want the semi-minor axis to find B. Minor axis has a length of 8, so we said semi-minor axis is half. So B is equal to 8 divided by 2, so B is 4. So our semi-major axis, we can figure that one out pretty easily because we want to find the distance between these two. So I can find that out by figuring out what's the distance between -2 and 8. So that's just 8 minus -2, if you think about your distance formula. So 8 minus -2, and then I'm going to divide that by 2, because it says semi-major. So the distance from -2 to 8 is going to be 10. 8 minus -2 should give me 10. And then divide that by 2 will give me 5. So I've got my A and my B so far. That's great. How do I find my center? Well, I need to remember that we said the center is the midpoint of the major axis. So I'm going to think center is the midpoint. So my major axis, the length is 5. So if I go 5 units over from -2, I'm going to go and land at the point 3, -1. If I think about it, if I go 5 units left from the other endpoint, 8, -1, I should end up at the same place. So my center is 3, -1. So now I have my h, my k, my a, and my b. H, k, and then a and b. So I can plug each of these into my formula and get the equation in standard form. So my equation in standard form is x minus 3 squared divided by 5 squared plus y minus -1 squared divided by 4 squared equals 1. And then we'll simplify it as much as possible. So our equation should have the form x minus 3 squared divided by 25 plus y plus 1 squared divided by 16 equals 1. So our standard form of the equation is this. It's simpler if we have an ellipse that's centered at 0, 0, because then I don't have to find the center, hk. So you can do it either way, but this is the more complicated version. So next week we'll talk about orbits and eccentricity and a few more things about ellipses, and we'll get into some space science. We can model the path of a planet around the sun as an ellipse. So we will talk about all of that next week. As always, take notes, email me with questions, and I will see you soon.